So let's take a look at some of the things that we can learn because of the laws of motion and conservation laws and law of gravity. So using the laws of motion, the laws of conservation, and the law of gravitation, we can actually explain all of Kepler's laws. So if you remember, Kepler's laws are the ones that deal with planetary motion. We've already explained Kepler's second law, why it is that planets speed up and slow down as they orbit around the sun. That's all about conservation of angular momentum. We can also explain the first and third law. Now, we're not going to get into the first law. To be able to explain the first law, we have to do all sorts of crazy math stuff. I've seen it. I've done it. We're not going to do it here. It's beyond what we can do in this class. But we can get a conceptual idea of how the third law works. Okay, so Kepler's third law is the one that describes how it is that planets are moving compared to each other. It's the one that states that the planets that are closer to the sun orbit faster than planets that are farther out. So in this case, we have two planets. We've got the green and we've got the white. The green planet is farther out, and notice it is orbiting slower. The white planet is closer in, and it is orbiting faster. So let's think about what gravity is doing. Which planet's going to have greater gravity? The one that's closer in. Remember, the farther away things are apart, the weaker the gravity on them is. So the planet closer into the sun will have greater gravity. If it has greater gravity, it will have a greater force, and then using Newton's second law, more force means greater acceleration, and if we have a greater acceleration, it'll be going faster. So using Newton's laws and the law of gravity, we can explain Kepler's third law. Now, to get the exact everything that's going on, it's going to involve way more math than what we're doing, but you can kind of start to see it conceptually. Now, as Newton was going through trying to explain Kepler's laws of planetary motion, he actually discovered several interesting things. One of these is that ellipses are not the only possible shapes for orbits. In fact, any of what we call a conic section is possible. Okay, so a conic section are the shapes you get when you take different slices of a cone. So if you slice directly across, you get a perfect circle. If you slice at an angle, you will get an ellipse. Okay, those two we've talked about previously. Remember, circles are a special type of ellipse. If you slice in other ways that actually go through the base, you can also form hyperbolas and parabolas. Okay, so all of these are possible shapes for orbits. Circles and ellipses are what are referred to as bound orbits. What this means is they actually orbit around the sun. They keep coming to the exact same place every time in their orbit. Parabolas and hyperbolas are what are known as unbound orbits. What that means is something is cruising through space, the pull of gravity changes how it is orbiting, and then it leaves never to return. It does not come back to the same place again in space. These are unbound orbits. Something else that Newton discovered is that objects don't actually orbit the sun. Instead, two objects orbit their center of mass. Okay, now, for me, what helped me kind of understand the idea of center of mass is thinking about a teeter-totter. Okay, so imagine you've got two first graders and they want to play teeter-totter. Okay, well, to get them to balance out, you have to put one on each side, and then they can go up and down and everything's good. They have a great time. Now replace one of the first graders with a sixth grader. The sixth grader is much larger. Because of that, they have to scoot in closer to that center point. That means that the center of mass is closer to the bigger kid. Okay, but if you get them positioned just right, then they're still able to balance and go up and down. That center of mass is the balance point between the two. Okay, it's where they equally balance, is on that center of mass. Okay, now, several years ago, I took my, at the time, 18-month-old daughter to a park. And I figured she would have a lot of fun riding on a teeter-totter. So I put her on one end, and then I went and sat on the other end of the teeter-totter. It went about as well as you can imagine. She learned a very important lesson that day. Don't trust Dad. Maybe that's a lesson you've also learned. Well, thinking about it, where should have I sat? I shouldn't have been over on the end. Because of how much bigger I was compared to my small daughter, I needed to be almost on top of the fulcrum. Okay? And if I was close enough in, then we could have balanced and gone up and down, and she would have had a good time. Okay? That, again, is the center of mass, and that is closer to what's happening with planets and the sun. The sun has way more mass than any of the planets orbiting around it. Because it has so much more mass, the center of mass is actually inside the sun. However, it is not the center of the sun. Okay? It's actually shifted out away from the center. What this means is that the sun is actually wobbling around that center of mass as the planets are orbiting around it. Okay? Objects actually orbit the center of mass. This is going to help us understand a lot more when we start talking about planets beyond our solar system, as well as what are known as binary stars. These are two stars that orbit around each other. Now, Newton also derived a version of Kepler's third law. Don't worry, we're not actually going to do it in class, but this is its form, and there are some things I want to point out. This p squared is the sidereal period. It's related to how long it takes for the planet to orbit around the sun. Now again, technically I should be saying how long it takes for the planet to orbit around the center of mass between it and the sun, but it's close enough for what we need. Over here, r is the separation, is the distance between the planet and the sun. Okay, but what I really want to point out is notice down here we have the mass of the sun and the mass of the planet. So what this means is if we know how long it takes for the planet to orbit and how far away it is from the sun, we can actually figure out the mass of the planet, which is really cool. Again, that's going to help us later on when we start dealing with planets beyond our own solar system. Now, when dealing with orbits, as things are orbiting around each other, we actually need to look at the total orbital energy. The orbital energy is the total amount of kinetic energy and the gravitational potential energy, and it's going to determine the orbit of the object. Now, if we actually want an object to, one, begin orbiting, we're going to have to give it energy. If you remember back when we talked about Newton's cannonball, okay, that was the cannonball thought experiment we talked about previously, that was all about giving the ball enough energy. And once it had enough kinetic energy, it was going fast enough to actually completely circle around the Earth. Well, if we're able to continue to give it energy, we're actually going to see its orbits change. And this is exactly what we do with satellites orbiting around the Earth, and if we want an object to actually escape the Earth and travel to another planet. Okay, so we start out with the object on some given orbit. At a certain point in the orbit, we'll give it a boost, give it more energy, so it then transitions to another orbit. And if we give it even more energy, it will transition to a larger orbit. And then if we can get it going fast enough, give it enough energy, then it will transition from a bound orbit to an unbound orbit, meaning it will no longer orbit around the Earth. It will actually escape and never return. Okay? The velocity that it is needed to get it to escape is cleverly named escape velocity. Escape velocity is the velocity required to actually escape the gravitational pull of the object. So what we do to get satellites or other instruments from the Earth to another planet is we carefully plan the orbit and then give the object the right amount of boost at the exact right place in the orbit so that it reaches escape velocity and will leave the Earth pointed where the object is going to be eventually when the space probe actually gets there. So not only do we have to worry about how it is that it's leaving the Earth, we also have to worry about how it is that the other object is moving in space so that we can actually get the object to arrive at the right place at the right time. There's a reason why we call people who do this rocket scientists. This is not an easy thing. However, we've gotten really good at it. A couple of years ago, the Juno mission arrived at Jupiter, and it arrived at Jupiter within 1 second of what had been planned by the mission planners. Again, we're getting really good at this. All right, so another consequence that we see from gravity are actually the tides of the Earth. But before we talk about the tides, we're going to do another thought experiment. So in this case, we have 3 billiard balls, 1, 2, and 3, yellow, blue, and red. Okay, now notice their distance away from the planet. Which of these balls is going to feel the greatest pull of gravity? It's red, number 3. It's the closest to the planet. Being closer means we have the smallest distance and the greatest pull of gravity. Which one's going to feel the weakest pull of gravity? Yellow, number 1. It's the farthest away. Greater distance means weaker gravity. All right, so we have our 3 balls, and then we let them go and see what's going to happen. After a given amount of time, we see that the red ball has moved the most. If it has the greatest gravity, it will feel the greatest acceleration, so it will move the fastest, and in our amount of time, if it's moving the fastest, it will then travel the farthest. Okay, and that's exactly what happens. The yellow ball, feeling the weaker pull of gravity, will not accelerate as much, does not go as fast, and therefore does not move as much. And that's exactly what we see. The yellow ball has moved the least. Now, this is all comparing these balls to the distance from the planet. Now, instead of doing that, imagine you're sitting on the blue ball. If you're on the blue ball, what appears to happen to the red and yellow? From that perspective, it appears like the red and yellow ball separate. They begin to go other directions. All right, so with that understanding so far, we now have our 5th lecture quiz question. Which side of the Earth has a stronger force of gravity from the moon? A, the side near the moon. B, the side far from the moon. C, the Earth feels the force the same on both sides. Or D, there is no way to tell. Go ahead and think about it, and we'll discuss in just a bit. All right, so which side of the Earth feels a stronger pull of gravity from the moon? It is A, the near side. Remember, the shorter the distance, the greater the pull of gravity, and Earth is a wide object. So one side is close and one side is far. The side that's closer to the moon feels a greater pull of gravity. The side that is farther away will feel a weaker pull of gravity. And that helps us explain the tides. One side of the Earth feels a greater pull. The other side feels a weaker pull of gravity. Now, we are not outside observers. We are on the Earth, which means, from our point of view, we see one side getting pulled towards the moon, and then the other side is being left behind, similar to that yellow ball. Okay, so this leads to a stretching of the Earth, and it leads to 2 bulges in the oceans. We have a bulge on the same side as the moon, where the water is being accelerated greater, and we have a bulge opposite the moon, where this stuff is actually being accelerated less than the Earth and is getting left behind. So we actually have 2 bulges. So as the Earth rotates, we rotate into one bulge, then out of the bulge, then into the other bulge, and back out. This means that every day, every one rotation of the Earth, we actually have 2 high tides and 2 low tides, as we're rotating into and out of these different bulges. Now, the sun also plays a part of the tides. Now, the sun is much farther away, but it also has a lot greater gravity. The effect of the sun on the tides is about 1/3-ish, somewhere in that ballpark, of the effects of the moon on the tides. But it does have an effect. So what this means is if the gravity of the sun and moon act together, meaning in a straight line, then it will cause the bulges to get larger than normal. Wherein we have greater than average high tides, this is known as spring tides. And it's any time that the sun and moon are acting in a line. So we will have spring tides during 2 phases. Here you can see we have it during full moon, but we will also get spring tide during new moon. Now, if the sun and moon are acting perpendicular to each other, then they actually cancel out. The moon goes one way and the sun goes the other way, and it kind of evens out. So when this happens, we have smaller bulges than normal. This happens during neap tides. Okay, now, what phases of the moon are we going to get neap tides? It's when the sun, earth, and moon make a 90-degree angle. Okay, so what this means is we'll have neap tide during first quarter and third quarter moon. Now, these ideas of tides don't just apply on the Earth. We actually see it any time we have an extended object that is being pulled on by gravity. This actually leads to what we call the tidal force, which is where the pull of gravity is stronger on one side than the other, and it leads to a stretching. In this case, we have two galaxies. We have this larger galaxy and a smaller galaxy that is beginning to fall into the larger one. Notice that the smaller galaxy is actually being stretched out because the pull of gravity on one side is greater than the pull of gravity on the other, causing the whole thing to stretch out. This is the tidal force, and it's actually going to help us understand several things later on.